Hello, good morning, ladies and gentlemen. Be very welcome to this session of the International Solar Alliance Expert Training course. Today's session is going to be on smart grids and photovoltaics integration. My name is Arranz-Piera. Of course, the supporters of this expert training series are the International Solar Alliance, together with the Clean Energy Solutions Center and the Carbon Trust. For this lecture, for this session, we have the collaboration of the companies Trama Tecnoambiental and Aguasol. Just a quick overview of the training course modules. This course is composed of up to 8 modules, and this session is part of module 4, which is devoted to the technical integration of solar PV. As mentioned, this particular talk, I will share with you a reflection and introduction to the issue of smart grids. Very briefly, a few words about myself. I'm a project director, senior engineer at Aguasol, based in Barcelona, in Spain. We are an international energy consulting and engineering and applied research firm. My previous positions include collaboration with Trama Tecnoambiental in Spain, also in Spain, together with some other previous jobs. I have more than 20 years experience in the sector, doing projects, international projects all over the place. And for the last nearly a decade, I am also collaborating with the university, Technical University of Catalonia, as an associate researcher and lecturer. Before we get started, I wanted to ask you to spare a few seconds to imagine what do you see when imagine that I asked you, what do you see if I mention a smart grid? What is the image? What is the composition, the architecture that you see? I would ask you to spare some time thinking about a smart grid. All right. So our vision of a smart grid is like this. A network, a grid, a connection of different energy consumers and energy generation points, connected together and sharing, of course, power, electricity, but also other forms of energy, heat, cold, and also sharing data from domestic premises, houses, housing blocks, apartments, public or community premises, hospitals, schools, industrial premises, etc. And also electric vehicle charging stations. So after this first vision that we can all have on the smart grids, the different visions we can all have, very quickly, let me go through different points that I will cover in this talk. First of all, why do we need smart grids? Then I'll talk a little bit about the definition of smart grids, then the comparison of smart grids versus traditional grids. What are the focus areas of specialization that we can find in the world of smart grids, the technologies, the components that we can find in such areas, some specificities about the designs of the PV systems aimed at the integration into smart grids, advantages, barriers, few comments on costs and benefits, and then we will close the session with a description of 5 case studies. So let's get started with the talk. Why do we need smart grids? Well, since its inception, the power grid has been operating in a unidirectional way, from large-scale generation to distributed consumers along the grid. At the same time, we have some international momentum, maturity of consumers and policies in terms of decarbonizing our electricity sectors. And for that, there is a need to facilitate a higher penetration of renewable energy generation. And to facilitate that, the decentralization of such generation is an essential strategy. Of course, such a view or such a strategy of the centralized multiplicity of distributed generation points, sometimes based on a stochastic energy source like solar energy, for instance, is a challenge. Is a challenge for the current nature of our traditional power grids. In that sense, the future grids or smart grids have to be capable to enable demand response strategies, to be able to, as I just said, integrate higher penetration of renewable energy generation in a decentralized manner, but also the interaction with customers that can take decisions, that can opt to become to certain stage generators, small or micro generators themselves, to also integrate the electromobility. We can consider electric vehicles as a group or a very large scale group of moving batteries in our system, etc. But at the same time, power grids need to continue ensuring reliability of supply under certain conditions of quality. As I mentioned, solar PV is a stochastic resource, meaning that we cannot control with ultimate precision when we have it available and when we don't. So integrating solar PV generation brings in challenges for power grids in terms of system stability, power balance, the compensation of reactive power, frequency response, and so on and so forth. As I mentioned, consumers are also becoming more attracted, more informed, in terms of also playing the role of generators at the same time. This is why this term prosumers has been becoming more widely used. This is, of course, the contraction of producers and consumers. And as I just mentioned, the large deployment of electromobility requires that grids, requires that smart grids or grids to become smarter in the sense that they should allow optimization of charging and discharging routines of such an electro float of vehicles. Definitions, of course, as I hope you would have realized, the little exercise of imagining a smart grid, probably the image, the vision that I showed was different to the one you thought. So there's no, at the moment at least, there's no absolute and totally adopted unique definition of what a smart grid is. Several concepts of smart grids have been proposed, formulated, coming from different interests, different angles, of course. An example that I show in this slide, coming from our colleagues, the UPC research group, CITSEA, their proposal for a definition of a smart grid is that of a combination of hardware, management and reporting software built atop an intelligent communications infrastructure. At the same time, CITSEA, they stress already the fact of having a communications and information stream together with an electrical infrastructure, a stream of power, of electricity flow. Of course, such streams, such flows of power and communications, together with the principle of making systems cleaner, safer, more reliable and efficient at the same time. Other examples of definitions. I chose this one from coming from the industry, from company Indra. Apart from picking up the definition of or the two pillars mentioned in the previous concept, the power flow and the information flow, this two-way communication flows between generation and consumption. In this sense, from the industry side, there is another layer coming in, which is the potential of generating business applications based on this volume of data that will be generated and managed within smart grid. This is, of course, of interest to the private sector. There are several technical standards in the process of being developed by different standardization agencies. Different concepts, different stages of work, depending on the purpose, depending on the government or the set of governments that is promoting such a standardization exercise. But there are a couple of concepts that flag that are key to any of those standards development, which are the interoperability and the cyber security. This would be two key aspects of what a smart grid would be. Broadly speaking, interoperability would be the ability of two or more components or systems to exchange information and to use that information. Cybersecurity, probably it's a more commonly used or familiar term to all of us, understood as cybersecurity is normally understood as the protection of computer systems from damage or from theft of their hardware, software, or data, as well as protection of such computer systems from potential disruption or misdirection of the services that they are intended to provide. Apart from these two main concepts that, in my opinion, would be inherently related to any smart grid, some other commonly accepted features of smart grids would be that, well, smart grids are the future, are the next phase of the power grids, if not the present in some applications, but at least, commonly accepted, the future has to be smart. And the use of digital data, digital enabling technologies to control, to manage this massive volumes of data that will be generated. And not only to generate this data and store it, but to use it, to use it in a smart way, in an intelligent way to facilitate the operation of the grid. Also, flexibility is another of the commonly accepted features, giving opportunities both at the transmission and distribution levels. Also, bringing flexibility in terms of generation as well as in the consumption side, adapting to different capacities of power generation and capacities, different load curves, different patterns of consumption. Some other features would be that for the smart grid should allow higher penetrations of solar PV systems, as I mentioned in the introduction, tackling the stability issues, the operational processes that are a challenge or have been a challenge in the past, and also allowing the remote control of such PV generation being integrated into the grid. Another feature would be the monitoring and analysis, the control, the automatization, and in a way we could also use the word the intelligence of such grids in a way that they can be self-controlled and in that sense optimized a larger integration of distributed solar photovoltaic resources. Not only the generation resources, but also energy storage systems. To the extent that such a balance between generation, consumption, and storage is monitored, analyzed, well, the better the whole power system, the grid, can work, can operate in all fronts, the technical fronts, but also economic and the business proposition fronts, etc. Another accepted or commonly accepted feature is that, well, the smart grid sector is enjoying a bit of a boom. Most of the technologies that enable smart grids are commercially available and mature, but of course, it is a sector that is undergoing continuous development, and some of these technologies that experience very rapid improvements and month after month, of year after year, we see a very substantial improvement in the performances and the industry proposals and products we come across and we can integrate. Finally, another feature of smart grids is that, of course, talking about such a critical aspect as power grids for countries. Well, the local regulations, the policy aspects are also key to facilitate the proliferation or the installment of smart grids involvement and implementation. Yeah, so we could see, in fact, we are seeing smart grids being more pushed, developed, and adopted in some countries or in some regions more than others, thanks to this more enabling policies in some places and not in some others. Perhaps in this slide, as a way of summary, if you want, some of the features of smart grids are probably better understood or more clearly identified if we compare smart grids to traditional grids. Well, this slide can be kind of a summary. I will not go through all of these rows in detail, but we can recognize the concept that I have already mentioned in the previous slide. Yeah, a smart grid will have higher degrees of intelligence, of self-management, control, self-restoration capability in front of events. Sorry. Also, the issue of the communication ways. Traditional grids functioning in a unidirectional way, whereas smart grids are essentially defined or conceived to work in a two-way communication, generation to consumption, and also through storage. The role of customers in traditional grids are typically uninformed and non-participative. You don't have, apart from paying the electricity bills, not there are little other parts of other areas in which they can interact with the grid. Whereas in a smart grid, customers shall be informed and involved, and thus become more active consumers and eventually prosumers, also contributing to generate part of the power of the electricity in that grid. Same kind of ideas, but in this slide we can see them in a graphical way. The traditional grid, we see the unidirectional flow of power and information to some extent, whereas in a smart grid we see more of a circular flow or a multi-directional flow of power and information, if you want. Now moving on to the areas of specialization of smart grids. Well, I guess you will agree with me that after having seen the concepts and the ideas in the previous slides, smart grids are like a sector or an ecosystem, let's say, of different sectors, of different subsectors, right? Depending on the angle we look at the issue of a power grid, we can find different areas of specialization where we will see specific industries, specific products, technologies that play a part in the world, in the ecosystem of a smart grid. I've tried to collect and put in the next couple of slides the main ones. One first area of specialization would be that of distributed energy systems, from different sizes, from micro generation systems to large or very large solar photovoltaic parks or farms, together with other renewable energy source based generators, but also a distributed float of batteries, specifically thinking about electric vehicles, but also energy storage systems that can be sited in buildings, battery banks, etc. Another area, focus area or area of specialization is, of course, the transmission and distribution grid management, specific technologies or concepts, components in terms of monitoring, control, security of grids, whereas on the transmission or distribution levels. Another area of specialization is the market proposition that can derive from smart grids, which can lead to an increase of consumer choices and business possibilities in terms of enabling higher degrees of interacting in terms of users modulating their demand, but also in terms of the price of the electricity consumption and the choice of customers depending on the price of electricity at each time. Another area of specialization, of course, the software and hardware technologies and products that will need to enable most of the issues we've mentioned before, like energy dashboards, controllers, sensors, and all sorts of smart appliances that can facilitate some of the features we've mentioned before, specifically on closer to the customer side. The communication mechanisms, communication systems that specifically talking about smart meters industry that will need to be able not only to meter electricity flows, but also store data and be able to communicate and transmit such data to the different actors in the grid. Also the control centers at the utility side, the different technologies, power line communications versus or combined with wireless networking systems to enable these data transmission to control centers and back if necessary. Graphically, this slide, of course, complements the previous ones. We can see the different subsectors or areas of industrial specialization that give way to smart grid technologies and components. Renewable energy sources, smart metering, transmission, automation, intelligence, let's say, into the transmission or the distribution grids, demand response management sector, the smart appliances sector, electric vehicles, and also storage. Now, just a few references, more details, more complements to the technologies and components that are part of these areas of specialization in a smart grid. As I mentioned, we have the advanced metering infrastructure. Smart meters are evolving very rapidly in the market, in the sector. featuring higher time resolution in energy metering and energy measurement, of course regular communication of the energy usage data to utilities, and also informing consumers. So it's a two-way communication from utility to final consumers. Another set of technologies or components are the advanced electricity pricing systems, where consumer prices can reflect real-time generation costs, thus enabling consumers to shift consumption towards hours, decide the potential deferrable loads that could be done in a moment of the day where prices are low, instead of doing it in another moment of the day where prices are high, etc. Or also enabling higher degrees of renewable energy generation that could be also in the hands or the premises of the end customer. You can imagine solar PV system in a house roof, and that same customer could decide to consume his or her own PV system generation at that time, or store it in his or her own batteries, or if that happens in a moment where the electricity prices from utilities are low, then that could be the moment to consume from the grid and exchange or inject the solar PV generation into the grid, etc. There's a number of scenarios that can open, and the decision-making processes will be ultimately related to the price of electricity from utilities or from own generation at each time. In terms of demand response systems, of course, all techniques to reduce energy load during those periods of peak demand throughout the grid will be of interest, or to also reduce the energy demand in those moments of low renewable energy generation. So to try to match as much as possible electricity consumption, electricity demand with the renewable energy generation levels at that moment. These techniques or these technologies, these systems include options like the direct load control, automatically or intelligent control, let's say, voluntary load reduction systems, by which customers may take the specific decision, active decision to switch off specific appliances, or dynamic demand control technologies and systems and products. Some other technologies or components that are very much in vogue in smart grids are the forecasting solutions of systems. Of course, forecasting is a key aspect in solar generation. The accurate prediction of solar generation is, of course, essential to reduce the cost of the system generation needs, and also can help the management of the different resources that can be fed into a grid according to the expected demand. So with some days or hours in advance, if demand can be predicted together with the solar generation, well, a more optimized of this matching, a more optimized matching can be prepared and operated. Another set of technologies that are essential to the integration of PV into smart grids are the inverters. Later on, I will give more details on the inverter side, but of course, smart inverters can and shall mitigate the impacts caused by photovoltaic generation on the grid, the impacts in terms of transient voltage fluctuations, or steady state voltage problems, but also frequency deviations. So the inverters power conditioning equipment will be in charge to mitigate such impacts. And this is an industrial area of very much of interest for smart grids. Storage, we already mentioned. Different storage technologies, different battery products, lithium-ion based products, or the good old lead acid battery-based products, and some new innovative technologies are being developed, tested, validated, etc. Storage, of course, when we consider solar generation and integration into a grid, is essential due to the stochastic nature of the solar resource. Yeah. Another set of technologies or components are the microgrid themselves. Of course, microgrids are sections of the grid that can be disconnected from it and can operate in an island mode or an autonomous mode, and then under certain conditions of convenience, and then it can be connected again. Another set of technologies or industrial area are the VPPs, the virtual power plants, that consist in an aggregation of energy resources that are not necessarily together in the same geographical location, but cannot work off-grid, so they need to be connected and therefore can be treated by the grid operator as a larger resource or a larger consumption. Of course, these VPPs open the way to enable new or innovative business or management models, like the local energy communities with the participation of neighbors, of different community premises that could be working together in the same power sector, but having different formats or different. Some can be companies, some other can be families, etc. Mixing together different types of prosumers organized throughout a VPP can interact with a smart grid. Now moving into the specificities of solar photovoltaic designs to facilitate the integration into smart grids. As we mentioned continuously in this talk, smart grids are essentially based on a bidirectional or multi-directional flow of power and communication streams. In this case, the communication and this at least two-way flow of communication and power flows will need to be also present between the grid and the solar PV system. And as I introduced before, such capability will need to be managed, governed by the power conditioning equipment, by the inverters. Inverters are responsible for the transformation of the photovoltaic generation in direct current voltage into alternating current in the grid. We have a graph here where we can see schematically after the PV panels, we can have an inverter power conditioning system consisting of a DC-DC converter with a mission to boost and maximize the power point functioning of the PV panels, then together with the inverter, the converter DC to AC, then together with the proper electromagnetic filters and the connection to the grid. A few references on the types of inverters. I'm now going to describe briefly the different types of inverters, but in terms of cost, we have the central type of inverters, costing roughly, please don't take these cost references as exact, these are just references, ranges, roughly in the range of $8 per watt. Then the string inverters, roughly costing twice as that. And then the micro inverters, which are the inverters that are installed, that come together with each of the PV panels. That could be costing in the range of 5 times more than the central inverters. A few words about each type of inverter architecture. First of all, the central inverters. Of course, this is the cheapest option because it consists of a one main power conditioning system controlling multiple strings of PV panels. This is, of course, the typical setup in large PV power plants or solar farms or solar parks, and of course they are normally used in larger systems because of concerns of cost and optimization of the maintenance resources, etc. The second type of inverters or inverter architecture would be the string inverters, which are aimed at controlling all the different PV panels connected together in series in a same string. These kind of inverters will maximize the power that is going to be delivered by each string, hence improving the efficiency of the whole solar system, maximizing the efficiency of each of the strings. So, the advantage of this is that they limit the impact of an underperforming panel only to that string where the panel is installed and not affecting the other strings, which obviously increases the robustness of the system compared to the previous type of inverter where a non-performing or an underperforming panel in one string would affect all the strings connected together via the same central inverter. Of course, the drawback to that in a string inverter architecture is that for the same power convention, overall power conversion capacity, a larger number of inverters will be needed compared to a central inverter. Thus, this is why the cost of such architecture is higher than the central inverter one. And going further into that modularity architecture strategy, we will find the micro inverters, as I mentioned in introduction. These are the inverters that will be attached to each of the one inverter per each PV panel. Of course, that enables real-time efficient DC-AC conversion per panel. Let's not forget that PV panels are composed by connections of several photovoltaic cells. So PV technology is very modular one, right? And also microinverters will also enable the circuit protection per panel and optimize each panel, thus maximizing even more the production of the whole PV array or PV field compared to the other two types of inverters. But obviously, if we need to consider inverters for each of the panels, the cost will increase. This is why, all in all, the cost comparison of central inverters versus microinverters is that of 1 to 5 approximately. Now, moving on to the advantages of smart grid. Well, I think most of this has already been mentioned, but it's always good to refresh them or to keep them for your takeaways of this session. Smart grids, under the perspective of solar energy integration, enable a larger degree of optimization and penetration of distributed PV generators, which means also the prevention, the avoidance of having to introduce backup systems, probably based on non-renewable fossil fuel-based systems. The advantages of smart grid conception, again, to increase the reliability of the supply, the quality, and the stability. Again, the role of the inverters is crucial. They can also incorporate the virtual inertia control algorithms to help into stabilize the grid conditions when receiving the solar generation, and thus reducing the probability of grid outage occurrences and brownouts or even blackouts in the grid. Another key advantage that we want and we expect from smart grids would be to reduce the peaks in demand, therefore allowing peak shaving, providing demand and response alerts so that the users become more active and can act accordingly on their consumption, and potentially also on the generation with their own distributed systems. And that, of course, will reduce congestion costs, apart from the probabilities of outages mentioned in the previous point. Another advantage, of course, smart grids will be more resilient to disruptions, will be intelligent and therefore self-healing with mitigation measures against possible occurrences. The predictive maintenance can be enabled. There's also saving costs in terms of corrective maintenance, and also reducing the grid restoration times and the associated problems with grid restoration. The optimization of demand and supply at local levels, local distribution levels, of course, will reduce the transmission losses from larger distances. That would be a bit of a summary of the advantages. Now, having a look at the key barriers to smart grids. By now, we have an idea of the complexity of the innovations or the new systems and components that need to be brought into conventional grids to make them smart or turn smarter. Such a complex infrastructure, of course, has a cost and some learning costs, as novelties as they are, and some estimations of the cost coming from the US. Some estimations indicate that roughly $500 billion will be needed to turn all of the United States power grids smart in the coming decades. So we're not talking about small amounts of investment needed. That, of course, is a key barrier to the proliferation of smart grids. For instance, something as simple as the deployment of smart meters, you can imagine, times the number of customers in a grid. That is already a bit of an investment. Another barrier could be the need to standardize the technologies and technical protocols, as well as the communication protocols between the different components of grids. And again, that has issues of ownership and issues of geopolitics and geographical location, different areas of the world coming from different power sector standards or cultures, might not necessarily share the same views, at least in the early stages. So there is a need. This would be a barrier in terms of time. Yeah. time it will require to standardize and bring together all these different protocols. Another barrier can be, or is expected to be, the entry of new players into the grid sector. Potential conflicts of interest between the different actors, between utilities, regulators, and prosumers, customers becoming producers of electricity, or independent power producers, companies who are essentially focused and aiming to maximize the solar generation as generators. Of course, that would be their legitimate interest, probably linked to a business proposition, compared to, or versus, the legitimate or expected aim or main interest of the grid operator, which obviously is going to be the grid protection versus any other thing, probably. So a barrier to smart grids can be, the way that the extent to which this potential conflicts or clashes between legitimate interests of different actors are managed, dealt with, and put together in a symbiotic way. Other barriers, of course, linked to the main feature of cyber security of smart grid, are going to be the ownership and the access to data. Not only the access, but also the management of the data generated within the grids, the different actors involved in the grids, who is going to be keeping and securing such data, which sometimes can be personal data, sensible data protected by different policies, regulations. So it's not a straightforward issue that can be a barrier to the deployment of smart grids. Again, the security, privacy of users, cyber attacks. These days we are all familiar with some substantial problems with access to personal data in social networks, and all the associated damage and risks that these attacks can pose directly. And finally, also another key barrier to smart grid proliferation, of course, are the policies. We find these at the policy level. Local, national policies need to be worked out and adapted at the same pace, ideally at the same pace as the technology evolves. But I'm afraid, just like many other technological innovations, industry is quicker to develop and put technology and commercial products ready for the market. Industry is quicker in that sense than governments and policy sectors are, in terms of enabling the necessary regulations to make these technologies to untap them and to have them deployed at a large scale. So yeah, definitely the policy front is one of the key aspects to work on if we want to see smart grids booming or being more and more implemented in the short and medium term. Very quickly, some details on reflections on costs and benefits of smart grids. Of course, there have been already some applications of smart grids that have revealed substantial benefits that outweigh the investment costs, the high investment costs due to the complexity of the technologies and the novelty of the equipment that we mentioned before as a key barrier. However, in some of these cases, the rates of return on the investment, even though are there, they may be too low or not sufficiently, let's say, attractive to the private sector, which means that the role of the public sector administration to push, to lead these early stages of smart grid deployment is essential. There are benefits from smart grids that that include countable economic gains derived from the increase in grid reliability, the use of renewable energy reserves, the cutting down of imports of foreign energy compared to the use of indigenous local renewable energy sources, together with the reduction in the backup capacity and grid reinforcement investments. So some of these costs are clearly countable. Some other benefits are more difficult to evaluate, even though from a qualitative point of view, we can see that these benefits exist in terms of public health, derived from the reduction in air pollution and emissions, achieved by using smart grids and solar PV generation into smart grids. Of course, the degree to which we can learn from these early examples, projects on smart grids that we are seeing being implemented now, the degree to which we monitor them, we learn from them, will generate more spatial and data and temporal, data availability and results that they can help us to quantify such benefits. And after some years, we'll probably able to quantify this externalization or these external benefits derived from smart grids that at the moment are a bit difficult to quantify in monetary terms. All right. Now moving on to the final slides of today's session. Case studies of smart grids. The first one comes from the Netherlands, the community of the Ceuvel, which is a working space located in North Amsterdam in the Netherlands, in a former shipyard. Since 2012, at the Ceuvel, there is a local energy community operating, having several PV systems installed in different buildings, and they have even created a blockchain system that uses a token called Jouliette that the partners, members of this community use to manage and share the locally generated electricity. Of course, they use smart meters to record the data, to assess the energy balances and the energy bills that are paid with this token, the Jouliette. The Ceuvel is one of the first examples that are being monitored and studied in Europe regarding smart grids and powered with solar PV, and they operate independently from the national grid. Interesting from this case is that all the electricity they consume is sourced from renewable energy, and they have recently they have also included in the network battery and electric bicycles charging station, giving way to that part of the smart grid ecosystem possibilities that we mentioned in the beginning, the electromobility. Now moving on to another European example, this case from Greece, the town of Xanthi. There's another interesting, this example comes from European project called Integrity. This is an interesting example of a microgrid that is in fact a smart grid including 3 nodes. So it is a smart grid including 3 smaller microgrids, including several types of renewable energy generation, together with energy storage and auxiliary generator. And one of the microgrids in this system has a hydrogen generator that uses surplus generation from solar PV system and a fuel cell to regulate the production of electricity based on the generation and load conditions. So it is a multi-technology distributed energy sector or system example of a microgrid. The system also includes communication, automation, and monitoring infrastructure. And it is regarded as a very interesting architecture or example of what could be done for islands all over the world. Another example coming from this research project internally in the town of Severino, Marche, in Italy. In this case, the particularity of this case is that there are moments in which because of the energy demand is limited in this town, it's a small place, the generation capacity can exceed the demand levels, leading to a frequent reverse power flow and interaction of this grid together with the main national grid. Also, in terms of management model, a local distribution utility is managing this system. So there's also a good example in terms of innovative governance. And this project also addresses specificities in terms of grid topology, including advanced monitoring of the regional grid, some novel models of the prediction of the energy generation from the solar PV systems, the demand response strategy based on historical data, statistical analysis, forecasting, and also day-ahead grid topology optimization. So these capabilities of prediction and matching of generation with demand are very much assessed in this case study. So by all means, an interesting case study to follow in the coming years. Another case study from a town here very close to our headquarters in Barcelona. This is a pilot project being designed at the moment for a sports center, including a battery energy storage system of 25 kilowatt hour, together with a small PV system. The focus of this case study will be the energy storage system to be used as a backup system for emergency lighting and servers and computer servers in case of an outage in the grid. So it is a smart grid conceived from the point of view of a backup or an alternative to the conventional grid existing in the greater Barcelona area, providing ancillary services to the grid in case of demand response events like an excess load or a grid congestion, as I said, in the greater Barcelona area. So it's a small pilot project aimed at demonstrating possibilities in that sense. Again, like in the previous case in Italy, flexibility, that is key objective of this energy storage system, the forecast, the capacity to analyze current and projected power demand, also the projection on the solar PV generation side based on forecasting, weather forecasting, also the anticipation of the predictability of electricity costs in order to enable real-time pricing strategies as potential business propositions for utilities, and also the possibility to incorporate additional revenues associated with those ancillary services that will be provided by such an innovative energy storage system as a backup to the grid. Finally, one last case study, this one coming from the US, city of New York and Brooklyn. One of the neighborhoods in Brooklyn has become very, very well known or popular thanks to this blockchain example, the Brooklyn Microgrid project that brings together a community, a smart grid community with prosumers, with consumers having their own PV system. Most of them are neighbors, Brooklyn neighbors, up to 60 of them working together, brought together by this microgrid that currently covers about 10 blocks in this neighborhood. As I said, they manage the electricity by means of blockchain technology, similar case to what we saw in North Amsterdam, at Ceuvel. And they also consider electric vehicles charging stations. This project has been developed by the DSO Con Edison, the reports we are getting from this project are also very positive and very inspiring. So this will be it for today's session on PV integration into smart grids. Here you have the references, a lot of references of the different slides and information I shared with you. I hope you have enjoyed today's session. I thank you very much for your attention, and I hope to connect with you soon in further sessions of this International Solar Alliance training courses. Thank you very much and have a nice day.